So in this lecture, we're going to look at two integrals that we can evaluate using this substitution method, but they do it in kind of a creative way, a way that doesn't match that one part is a derivative of the other that we talked about in the previous lecture. So what I'm going to do here is it kind of, I think, hopefully it's a little bit the obvious thing at this point. I'm going to let u equal x minus 1, because if I can make that the square root of u, I know what that is. That's a power rule situation. Okay, so if I make that substitution, this becomes the integral of x square root of u dx. Now, here's where things get interesting. du is equal to dx. Yeah, so I can make that substitution, and that would be fine, but I still have that x floating around it there in front. That didn't get eliminated like it did in the previous examples that we looked at. So here's what I'm going to do. I'm going to take that substitution, that u equals x minus 1, and I'm going to solve it for x. And we get x equals u plus 1. So there's my two substitutions. I'm going to replace dx with du, and I'm going to replace x with u plus 1. And this is what we get. Right? It's the integral u plus 1 times u to the 1/2. I went to a fractional exponent, times du. Now, if we multiply this out, if I distribute that u to the 1/2 into the parentheses, this becomes u to the 3/2 plus u to the 1/2. And I know what to do with those. Those are both just product rule situations. Right, so I'm going to do each of them separately. U to the 3/2 becomes 2/5 u to the 5/2. U to the 1/2 becomes 2/3 u to the 3/2. And of course, we've got that constant on the end. And now I just have to go back to x's. I'm going to replace the u's with x minus 1. And this becomes 2/5 x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus a constant. Definitely not what I think anybody might have expected. That's a really strange result, that the integral of a product should end up being a sum like this. That's kind of unusual. But if you're doubtful, remember you can always check your work here. Right? If you differentiate that expression, you should end up back with x times the square root of x minus 1. Okay, so how about this one? I want to integrate the square root of 1 minus x squared dx. It's the equation of a unit circle, essentially. So here's what I'm going to do. I'm going to make a substitution that may seem very non-intuitive at first. I'm going to let x equal the sine of theta. Right? Because I'm thinking ahead here. If I put the sine of theta in there, that becomes the square root of 1 minus sine squared theta. Well, let's actually go ahead and do it. That becomes the square root of 1 minus sine squared theta cosine theta d theta, because that's dx. Right? If I differentiate my substitution. Now, here's why I did that. The square root of 1 minus sine squared theta. 1 minus sine squared theta is cosine squared theta. And the square root of cosine squared theta is cosine theta. Times the cosine theta that's outside of the square root, this becomes the integral of the square root of cosine squared theta d theta. Now, it might not be obvious how that helped, right? Because I don't know what that is. I don't know a function that if I differentiate it, I get cosine squared. Well, here's what I'm going to do. I'm going to do a trig substitution, right? Cosine squared theta is equal to cosine 2 theta plus 1 divided by 2. Okay, well that's looking a little better. Now I'm going to split that up. Integral cosine 2 theta over 2 d theta plus the integral of 1/2 d theta. Okay, that integral 1/2 d theta, that's easy. The other part we're going to have to work out a little bit. I'm actually going to do a second substitution here. I'm going to let v equal 2 theta, which means dv equals 2 d theta, differentiate both sides, or d theta is dv divided by 2. All right, so let's make that substitution. right? If I substitute that just into the first integral. The second one I'm not concerned about. It's the first one we're going to have to work at here. This becomes cosine v over 2 times dv over 2. All right, so let's pull the constants out. That part becomes 1/4 integral cosine v dv, and I know what that is. I know a function whose derivative is the cosine. It's the sine. Right, so this becomes 1/4 sine of v plus, and I went ahead and did that second integral now, 1/2 theta, of course, plus a constant. Okay. It's good that we've gotten rid of the integrals. That was progress. But now I've got this weird mixtures of v's and thetas, and all I want are x's. Okay, so here's what we're going to do. Okay, so here's what I'm going to do. On the top line here, I have the original integral and our two substitutions. And remember, 1/4 sine v plus 1/2 theta plus c. That's where we ended up after doing the integration part. So here's what I'm going to do. First, I'm just going to put 2 theta in there for v. Right, so this becomes 1/4 sine 2 theta plus 1/2 theta plus a constant. Good. Now I'm at least down to just one variable, even if it's not the one I want. So remember, sine 2 theta, that's 2 sine theta cosine theta. So the integral is now 1/4 2 sine theta cosine theta plus 1/2 theta plus a constant. All right, that sine theta, I can fix that easily. That's just x. Right? How about the cosine theta? Well, go back to our x equals sine theta part. If I square both sides of that, it becomes x squared equals sine squared theta. Now remember, sine squared theta is 1 minus cosine squared theta. All right, now if I solve this for cosine theta, right, I'm going to move the cosine over. I'm going to move the x squared over, take the square root. This becomes cosine theta equals square root of 1 minus x squared. Excellent. Now I've got my sine theta taken care of. I've got my cosine theta taken care of. How about this theta part? Well, again, now go back to that x equals sine theta again. If we solve that for theta, we get theta is equal to the inverse sine of x. And that fixes my 1/2 theta issue. Right? I'm going to make all of those substitutions into that integral, and this becomes 1/2 x square root of 1 minus x squared plus 1/2 inverse sine of x, again, plus a constant, right? And that's my answer. So hopefully, hopefully at this point you're starting to get your head around the idea that integration is not as straightforward as differentiation, right? The integral of what appears to be a relatively simple function, like I said, is just the equation of a unit circle. It can end up being something really kind of on the complicated side. Okay, now that we've got some practice evaluating integrals, and we've got a couple of tools for doing this in our toolbox. In the next lecture, we're going to give the integral of a function a physical attribute. Remember when we talked about derivatives, started off being a little abstract, but then when we started thinking about it, we said, well, look, this derivative represents the rate of change of a function, kind of a physical attribute. We've got something similar with integrals. Integrals, as you'll see in the next lecture, and a couple lectures after that, we're going to spend a little time developing this. The integral of a function represents the area under that function.